The main job of the lungs is gas exchange, pulling oxygen into the body and getting rid of carbon dioxide. Normally, during an inhale, the diaphragm contracts to pull downward and the chest muscles contract to pull open the chest, both of which suck in air like a vacuum cleaner. And then during an exhale, the muscles relax, allowing the lungs to spring back to their normal size and push that air out. But as it turns out, not all the air that we breathe in ends up participating in gas exchange. As we inhale, air enters the nasal cavity or the oral cavity and travels down the trachea, and then splits into the two main stem bronchi and enters the two lungs. Within the lungs, the bronchi divide into progressively smaller and smaller bronchioles until air gets down to tiny, thin-walled air sacs called alveoli, which are surrounded by tiny capillaries. And this is the site of gas exchange. So the part of the respiratory tree prior to these alveoli, starting from the nose or the mouth, right up to the tiny terminal bronchioles without these alveoli, merely acts to conduct or transport air to the alveoli. This part is therefore known as the conducting zone, and it doesn't take part in gas exchange. The volume of air contained in this conducting zone is known as anatomic dead space. Dead sounds kind of ominous, but it basically reflects the fact that this air is as good as dead to the body, because you can't extract oxygen from it. Anatomic means that this dead space is inbuilt within the anatomy of the respiratory system and doesn't really change. No matter what we do, we can't ever use this air for gas exchange. Alright, so now let's simplify all this. So this ball represents all of the alveoli, and this portion represents all of the conducting zone. In other words, the anatomic dead space. So how much air is part of this anatomic dead space? Well, a normal person, when breathing quietly without any active effort, takes in about 500 milliliters or half a liter of air. And this is called the tidal volume, represented by these three blocks. Almost a third of this tidal volume, or about 150 milliliters, is trapped in this anatomic dead space. And the remaining 350 milliliters or so is used for gas exchange. Okay, so let's rewind way back to when an infant is born. At this point, there's no air inside the lungs, so the alveolar air sacs are completely collapsed. As the baby takes in its first breath, new oxygenated air, shown in purple, rushes in through the respiratory tree and inflates the alveoli. But about a third of that air is left in the anatomic dead space, shown in orange. But we'll keep it half purple to show that this is still oxygenated air. Those purple blocks then participate in gas exchange, converting them to old deoxygenated air, shown in green. As the baby starts to exhale air for the first time, this dead space air, which didn't participate in gas exchange, is the first to be exhaled out. And then the conducting zone gets filled with air from the alveoli, which has already taken part in gas exchange and has given its oxygen to the body. During the next inhalation, it's this old green deoxygenated air that re-enters the alveoli first, and it's joined by fresh oxygenated purple air from the new tidal volume. Now again, that dead space gets filled with fresh air that has just been breathed in. This goes on for every subsequent breath cycle throughout the life of the person. So to summarize, if you sample the dead space air after a person has just inhaled, then the dead space air would be fresh air from the environment. And if you sample the air from the dead space after a person has just exhaled, then the air would be from the alveoli. So to gauge how effectively gas exchange is taking place in the lungs, it's important to time it just right, and take the air sample from the dead space at the end of exhalation. Now, so far we've been assuming that the air that manages to reach the alveoli is able to participate in gas exchange. Unfortunately, this isn't always the case. Some alveoli might have an inadequate blood supply. So when these alveoli get filled with fresh purple air, they're well ventilated, but they're not well perfused. This is known as a ventilation perfusion defect. In this situation, the oxygen in the purple air doesn't functionally make its way into the blood. So some of this air also ends up being dead space air, but this time we call it alveolar dead space. And together with the anatomic dead space, we call this physiologic dead space. The term physiologic refers to all the air that's physiologically inaccessible to the body due to anatomic and functional reasons. Okay, so now that one block of accessible fresh purple air gets exchanged and turns green, and then these 3 blocks get exhaled. We can actually now use some fancy equations to calculate the volume of physiologic dead space of the exhaled air, which we'll say is V for volume sub D for dead space. But first, there are a couple important assumptions. The first is that we assume that there's no carbon dioxide in the environment air. The actual figure is about 0.04%, so 0 is not too far off the mark. And remember that this is the half purple boxes here since that air came from the environment, but was never exchanged. Assumption number 2 is that none of the carbon dioxide was contributed from that dead space, which would again be these half orange, half purple boxes. So based on assumptions 1 and 2, the purple and orange blocks have 0 carbon dioxide. That leads to the third assumption. All the carbon dioxide in exhaled air comes only from functioning alveoli. In other words, this last green block. Now, if the tidal volume is volume sub T, the volume of air trapped in the physiological dead space is volume sub D, and the volume of air present in the functioning alveoli is volume sub A, from this it's pretty clear that Vt equals Vd plus Va. Now let's say that the concentration of carbon dioxide in the tidal volume is C sub T, and the concentration of carbon dioxide in the alveolar air is C sub A. Now, if you take a volume in milliliters and multiply by the concentration in, say, milligrams per milliliter, then you end up with the total amount of that something m, in this case measured in milligrams. Now that means that the total amount of carbon dioxide in the alveoli is the volume Va times the concentration Ca. Similarly, the total amount of carbon dioxide in an exhalation is the tidal volume Vt times the concentration of the tidal volume Ct. Remember though that one of our assumptions is that all of the carbon dioxide in the tidal volume is from the functioning alveoli, in other words, the green block. We could add in the concentration Cd of the dead space, but remember that it's equal to 0. So really the total amount in the tidal volume is the same as the amount in the alveoli. So we have Ma is equal to Mt, or concentration of alveoli times volume of alveoli is equal to the concentration in the tidal volume times the tidal volume. With a little rearranging, we have Va equals Ct over Ca all times Vt. Now that we have Va, we can substitute that guy in our original equation, and we'll end up with the tidal volume equals the volume of the dead space plus the tidal volume times the concentration of the tidal volume over the concentration of the alveoli, which can be rearranged to be the volume of the dead space equals the tidal volume minus the tidal volume times the concentration of the tidal volume over the concentration of the alveoli, which is also equal to the tidal volume times the quantity 1 minus the concentration of the tidal volume over the concentration of the alveoli. Now let's multiply all of this by Ca over Ca, which we can do because anything over itself is just equal to 1. After distributing Ca over Ca, you get Vt times the quantity Ca over Ca minus Ct over Ca. And finally, at long last, we have the tidal volume times the quantity, concentration of the alveoli minus the concentration of the tidal volume, all over the concentration of the alveoli. Now, anytime there's a mixture of different gases, the partial pressure of any one of the gases is directly proportional to the concentration of the gas in the mixture. So, for example, as the concentration of carbon dioxide increases, so too does the partial pressure. To convert this proportionality into equality, we need to multiply by a proportionality constant K. So we get partial pressure times K is equal to concentration. Now let's apply this equation to our previous equation. We end up with the volume of the dead space equals tidal volume times the partial pressure in the alveoli times K minus the partial pressure of the tidal volume times K all over the partial pressure of the alveoli times K. Conveniently, you'll notice that all our constants actually just cancel out. So you just end up with the volume of the dead space equals the tidal volume times the partial pressure in the alveoli minus the partial pressure in the tidal volume all over the partial pressure in the alveoli. Now, in well-functioning alveoli with adequate blood supply, carbon dioxide quickly dissolves into the blood until the partial pressure of carbon dioxide in the alveolar air is equal to the partial pressure of carbon dioxide in the blood, which can also be written as P little a CO2, little a for arterial. So we can replace P big A with P little a CO2. And this final equation is known as the Bohr equation and is used for calculating physiological dead space. And it's named after the Danish physician Christian Bohr, father to the more famous son, physicist Niels Bohr. Alright, as a quick recap, we can't use all of the air we breathe in for gas exchange. About a third of the normal tidal volume, or 150 milliliters, is wasted on its way to the alveoli and makes up the anatomic dead space. In addition, some of the alveoli don't get adequate blood supply, and therefore they don't participate in gas exchange. When we add this air wasted in non-functioning alveoli to the anatomical dead space, we get the physiological dead space. And the physiological dead space is calculated using the Bohr equation.